Hey guys, I'm joined in my sunroom by Gandalf. Gandalf is our house bunny. Isn't he adorable? Hopefully he will not be. I know you guys are just going to watch him the whole time I talk, and I'm just going to be up here like Charlie Brown's teacher while you look at cute little Gandalf. He's awesome, actually. I wanted to talk with you guys just briefly about carbon-14 dating. See, the printout that I gave you guys is from a secular evolutionist textbook that presents carbon-14 dating as an absolute. That is not, in fact, true. So carbon-14 dating is set up to measure the amount of carbon-14 that has been transformed into nitrogen. Really cool transformation. It's a great process, but the question that you have to ask yourself when you're looking at this is, when we did the triangle and we said, all right, so you need the total amount and you need the number of half-lives that have passed and you need the length of the half-life, but you have to have the total amount of time. They are trying to take that equation and then backtrack how much carbon-14 they expect to be in a particular sample. The problem with this is that unless that sample is about 5,000 years old or younger, it becomes wildly inaccurate. You guys have a lab where you are looking at inverse proportions. It's the flashlight lab. And what you'll see when you do that inverse proportion is that an inverse proportion, the graph goes like this. It makes a curve, okay? So at time of zero, the jumps in carbon-14 are actually pretty big, so it's not hard to get fairly accurate measurements of how much carbon-14 is in a substance. Not only that, but we have relatively recent samples to compare them to that are all under the same conditions. The farther out you get, the less accurate it gets, because the jump on the x-axis represents such a small change, an ever smaller change on the y-axis. I hope that you've talked about this in Mr. Ellis's class at some point. The reason that that's important in carbon-14 dating is that you're already talking about fractions of milligrams, and now we're trying to measure something that is decreasing in an ever smaller fraction of a milligram. So any inaccuracy in our measurement can result in thousands of years difference. And the only way that we even have a carbon-14 graph is that we've taken samples of different things that we do know how old they are. For instance, you can tell exactly how many years old a tree is. Well, if they cut down the tree and take a sample from that tree and they actually count the rings and find out how old the tree is, now you have a great sample of how much carbon-14 would be present in that particular sample at that particular age. So we've taken things that we know the age of because we can verify them with outside sources, and then we've made a graph that shows the basic trend of carbon-14. If an item fits into that graph, great, it backs up our theory of carbon-14 dating. If that item does not fit into our graph, then we call it an outlier. At that point, we have no explanation for these outliers, but I can tell you that the older a thing is, be it a rock, well, you can't carbon-14 a rock. Carbon-14 only comes from living tissue. Rocks don't count, sorry. A tree, a fossil, something like that was at one point alive. If you date that and that thing, the older that thing is, the less reliable carbon-14 dating becomes. So carbon-14 dating has its uses, but those uses are within the first half-life of carbon-14. Past that first half-life, the amount of carbon-14 that degrades is almost so small as to be immeasurable, and it becomes extremely unreliable. I just wanted you guys to know what the deal is with carbon-14 dating. Our book, like I said, presents it, or not our book, this packet presents it as fact. It's really not a strong enough theory to be considered a fact yet. From me and from Gandalf, can you say bye, buddy? See you guys later.